In this last part, I will discuss the educational implications of the conceptual framework I elaborated in part 2. Think, for instance, of this conceptual matrix. By arranging the three main settings, field, lab, and center, against three important aspects of the scientific work in each setting, we are forced to assess the corresponding levels of activity in each cell. Those levels could in turn be quite revealing for curriculum design efforts. For example, using the matrix, we may want to focus on one context or setting. For example, labs, a vertical move, and think of what are likely to be the demands in terms of the activities that take place in that setting for students. This approach may suggest that in terms of lab work, we could design environments or lab activities for students where joint activity might be low, but the demands for working with materials and representational systems is quite high. At the same time, we should expect a moderate level of understanding among students on how their particular lab activity relates to the claim-making process. In an alternative fashion, we may want to move horizontally or think of one aspect of scientific work across several settings. Think, for instance, of how we may have to arrange resources at each setting for students to develop the demanded or expected level of intercontextuality. It is clear from the matrix that work at the center demands a high level of intercontextuality, or the ability of students to know how a particular piece of data relates to work upstream, that is, work that was done at labs and field sites. Next, I will illustrate how I have used this framework in several educational settings. I use this framework matrix for thinking of how best to engage underrepresented Hispanic and African American students in an after-school program I conducted in California called Diving into Science. The program relied on creating some initial engagement with the tools of science in the context of field work. That seems like a good, engaging idea for students who had been traditionally left out of the science in and out of schools. The work they did centered on field work, as I mentioned. Lab work and center work were less of a focus, and thus represented by thinner or colorless arrows. These students helped calibrate underwater instruments used by marine scientists in California. Students in this program really showed a significant increase in academic engagement with the school science. Their perception of science and scientists changed radically. This was an important development for this type of underrepresented students. However, their knowledge of lab and center work remained quite embryonic, as the conceptual framework will seem to indicate. Another example was a curriculum effort that we call review encounters. These were carefully designed events in which scientists or professionals met with the students to critique the development of a particular student-generated project. They were intended as moments in which interactions between newcomers to a discipline, students, and old-timers, scientists or professionals, discuss the value or merit of a particular design or approach to a problem. These events resemble work we saw taking place at the center, at the back house. Those discussions, while often quite productive in terms of generating moments of explanatory power among students, seem to also lack disciplinary depth. In short, students often offered justifications for their approaches that did not align well with knowledge of the organism they were working with. This, in my view, was partly due to the nature of the curriculum. For instance, the fieldwork aspect of this project-based curriculum was quite thin if one compares it with the mature practice. In fact, students never had systematic and real access to any natural phenomenon. A hypothetical problem stood for fieldwork. Likewise, lab work consisted of producing a computer model of a population growth. As I have shown, the conceptual framework is useful in helping us identify aspects of a school-based science curriculum that may better represent adult practice. But it also points to aspects where much more work is needed in curriculum implementations. I want to close by offering a set of generic, design-oriented questions and statements one can produce with this framework. For instance, we can start asking comparative questions. How are or could the type of activities and contexts or settings represented in school science? Now, we know that most schools cannot replicate the settings we saw at the Bug House, at least not on a permanent basis. We might be better off asking or comparing the type of leading activities and the way people use resources to, for example, do field work or lab work. In other words, it might be more productive to think of accessing, transforming, and representing the organism. We may also ask about the volume of work done across the settings. At the Bug House, there is a cone effect, so to speak, with lots of field work and much less work done at the center. I think in schools, the opposite effect takes place. Students often collect data very quickly and then spend quite a bit of time discussing their observations. While I don't think the volume of work can or should be replicated in a school, we should nevertheless think about what should it means for the production of scientific claims and how it could be adapted within the school constraints. Another fruitful issue might be the conceptual nature of the work done at each context or setting. Let me explain. Think of this diagram as illustrating the nature of work done at each setting. On the left is the work at field sites, where you are dealing mostly with the material or concrete aspects of the work, termites, wood, dirt, plastic bags, etc. As the work moves to labs, we begin to transform these materials into signs, as I propose. Now, inside labs, one value stands for all termites at one location. On the right, we have work at the center, which is primarily concerned with making universal statements. These are statements of generality. For instance, a chromatogram or a chart defines all individuals of one species. From a curriculum perspective, this model forces us to re-examine notions of disciplinary learning that have relied heavily on aspects like hands-on learning. This model suggests that sustained periods of time or extended organizational structures on the materiality side of the spectrum will result in good understanding of the organism, but perhaps in a weaker mastery of generalization, or in students' ability to theorize about a particular category. We may also think of how is the coordination across contexts supported in school science. These are questions that can be quite productive for designing learning environments in a school. I thank you very much, and I hope this initial work can be of help to those trying to understand scientific practice and with the aim of reforming our schools.